forces. Intermolecular forces, like we said last week, always take place, or the majority, 99% of the time, are going to be taking place in liquid forms. Solids have crystal structure that they don't move, they only vibrate. Gas particles are so far apart that they're not going to relate to each other or be attracted to each other on a molecular basis. You have to get molecules that are freely moving as well as close together in order for this idea of intermolecular forces to be taking place. The different types of intermolecular forces, we talked a little bit about ion-dipole interactions. Remember, in ion dipole and dipole-dipole, those are two that can exchange places in terms of their strength. Sometimes ion dipole can be stronger than dipole-dipole interactions, and sometimes the reverse is true. It just depends on how polar the molecule is. This is one way to classify the intermolecular forces, just listing them. Another way we looked at last week in terms of the strength of the intermolecular forces, remember the strongest of all is hydrogen bonding, which is a subset of dipole interactions. Then ion dipole can sometimes compete, and then finally London dispersion forces are at the bottom. Another way I was thinking about, in order to classify these kinds of things, might be a way to think about how intermolecular forces are in terms of how would you decide what kind of substance or what kind of intermolecular force a substance has. All right, so if we look at the umbrella of all intermolecular forces. Remember, these are not bonds. This is not ionic bonds. This is not covalent bonds. This is all just forces between molecules that are attracted to each other. One of the first questions that you might ask yourself in the flowchart situation and say, all right, one of the things you're going to have to do on the quiz, one of the things you're going to have to do on your exam, both the exam for this class as well as the ACS final, is you're going to have to identify the type of intermolecular force that might potentially be present in a liquid. All right? The very first question you have to ask yourself is the liquid polar or is it non-polar? If it is a substance that is polar, meaning you have to draw the Lewis structure, you have to look at the electron configuration and the electron geometry as well as molecular geometry, and then you have to decide if it's polar. If it's polar, then you're going to have either dipole interactions, or you're going to have ion-dipole interactions. Now, dipole-dipole interactions, remember you have to have things that are polar, like water has dipole-dipole interactions in it because water molecules are very polar. Ion dipoles, you have to have a polar substance as the thing that is doing the dissolving, as the solvent, right? So you have to have something that is a polar solvent, and then that polar solvent, you have to put something in it that is soluble and creates ions. And sometimes the ions are only +1 ions, and sometimes they're +2 ions, and it depends on the ion. You know, if it's a plus ion versus a minus ion, the higher the charge of the ion, the more intense the ion-dipole interaction. Right. If they're nonpolar molecules, the only choice you have are the London dispersion forces. And these ones are very strong because polar molecules have a strong attraction for each other, and these are very weak, wimpy intermolecular forces. Right? Ion-dipole interaction, or excuse me, dipole-dipole interactions, the biggest and strongest of all the intermolecular forces is this thing we call hydrogen bonding. And I wish the chemists and people who had, yes?
So is hydrogen bonding kind of like a subset of dipole-dipole?
Exactly. Hydrogen bonding is a special case of dipole-dipole interactions in which the dipole molecules are super polar because the thing that hydrogen is hooked up to is very electronegative. So this hydrogen bonding idea, it has to be hydrogen bonded to either nitrogen, oxygen, or fluorine. Now, I didn't mean to put those, I should be or. I don't want those to look like bonds, right? So it has to be bonded to nitrogen, oxygen, or fluorine. And remember, if you think about the trend in electronegativity, ionization energy, electron attraction. The trend is bottom to top and left to right, with fluorine being the most electronegative element of all. Right next to fluorine is oxygen, and right next to oxygen is nitrogen. So you can see why if hydrogen, which is way on the other side of the periodic table, remember the rule of thumb to determine how polar a particular bond is how far away are the atoms from each other on the periodic table. Fluorine and hydrogen are really far apart from each other, so that's a super duper polar bond, especially because fluorine is so electronegative. Oxygen's a little closer, not quite as polar. Nitrogen is a little closer, not quite as polar. But those are the three things that have to be hooked in. It has to be bonded, and I'm going to put a little caveat here, it has to be bonded directly. And make sure you add that directly to nitrogen, oxygen, and fluorine. It can't just have nitrogen, oxygen, and fluorine in the molecule and have hydrogen in the molecule. The hydrogen has to be bonded directly to the nitrogen, oxygen, or fluorine atom within the context of the molecule. All right, so that's one way to think about how to classify the types of intermolecular forces a particular liquid might have.
So going back to ion dipole, it's going to be a polar solvent plus the soluble
Ionic salt.
ionic salt.
We are using a whole lot of vocabulary words in this class now. If you came into this class right now, with your knowledge that you had 14 weeks ago, what I'm talking about right now would make no sense whatsoever, right? Now, because you have all this chemistry knowledge, I can say things like a dipole solvent and a ionic salt. Remember, ionic salt is anything metal, non-metal. It could be binary ionic, it could be ternary ionic, but if it's soluble, that means it's going to create the ions in a polar solvent. And that's why water's called the universal solvent. It's so doggone polar that it can break up almost any ionic salt that is, available to it. Here's the symbolism that they're showing you with ion-dipole interactions. There's a negatively charged ion in the middle, and then they're making a blob to show any molecule that's polar. It could be water, it could be ammonia. Anything that's polar is just a blob of polarness. And you see that the negative ion is the positive one oriented towards it, and the positive ion has the negative side of the polar solvent oriented towards it. And then we talked about these dipole-dipole interactions, and it depends on the polarity of the individual molecule, how strong the individual dipoles are. You can have dipoles between water molecules, you can have dipoles between unlike molecules like water and ammonia. Now if we look at these things here, this is a group of molecules there's a couple of questions that are specifically about this group. So I'm going to encourage you to write down the molecular structure as we talk about each of these molecules, because it's really good to illustrate this idea of dipole-dipole interaction. So molecules that are polar. Now if you look at each of these, and if we use that original chart that I talked about today in the umbrella of intermolecular forces, we could look at each of these things and we say, all right, they're all very similar in molecular weight. If you look at that first column after the substance, the molecular weight of most of these is between 41 and 50, so there's within 20% range of each other. Dipole moment has to do with how polar that particular molecule is. Now, it is a way to calculate this. There's a chart that gives the dipolarity of each individual molecule. There's this very simple calculation that you arrive at, but suffice it to say that the larger the value of the dipole moment, the more polar that molecule is. And then we're going to talk about things like boiling point in just a minute. All right, so let's go through each of these molecules. I want you to draw the structures because this is important to compare these things. The first one is propane. We're going to get a little mini lesson on organic chemistry as we're going through this. So how many people in here have to take organic chemistry at some point? Yeah, not my favorite. If you're good at memorization, organic chemistry is going to be a piece of cake. I can't think of a single bit of math associated with organic chemistry. That's probably why I didn't like it, because I'm a math kind of girl. All right, if you are a physical chemist like myself, we simply care about the actual formula for the compound. In propane, it's C3H8. That's how a physical chemist like myself would describe propane molecule. Now, we can get, you are used to propane being in gaseous form, right? But if we put it under high pressure and low temperature, we can get it down to a liquid form. So now we're talking about propane being a liquid. An organic chemist would write the chemical formula different an organic chemist would give you some information about what the molecule looks like as they write the chemical formula. This is more of what's called a structural formula, and this is more of what you might call a chemical formula. You can see it's the same number of carbons and hydrogens, but the way an organic chemist would write it, and when you get into organic chemistry, they would expect you to write it like this, because the way that the molecule is put together. So if you did the Lewis structure for this, this is called a long chain hydrocarbon. It's got 3 carbons right in a row, and you can see there's a CH3 on one end, and then you got a CH2 in the middle, and then another CH3 in this direction. If you did the Lewis structure, you count up all the valence electrons for the 3 carbons and all the hydrogens, and you distribute them all, it would look like this. Now, that's really not the best way to depict it, because you know that each of these, because they have the tetrahedral electron geometry around each of those atoms, actually looks kind of like this. And when hydrocarbon chains are long chain hydrocarbons, organic chemists will draw them like this, but in space, you know, they're actually looking more like this. They're sort of bent back and forth. All right, so if this is propane, is that, if we looked back at our original classification and how to determine what kind of intermolecular forces a particular substance has, is this molecule, is propane going to be polar or is it going to be nonpolar? It's going to be very nonpolar. There's no non-bonded pairs of electrons anywhere sticking out. There's no very electronegative atom or portion of the molecule. It's all very, very neutral and very, very symmetrical. All right, so this would be nonpolar. So if it's nonpolar, what's the type of intermolecular force that it could have? The London dispersion forces, or the dipole moment. Now, let's sort of step back and talk about London dispersion forces. There's 2 ways. London dispersion forces happen in a non-polar molecule. What happens is, what's created is what's called an instantaneous dipole. I'm writing that very good. Instantaneous dipole, meaning just for a split second in time, a molecule could be slightly polar. For example, if we had a gas, if I had something really non-polar, like a noble gas, for example, if I had something like a monatomic gas like argon. There's a simple argon gas molecule right there, a single atom of argon. Actually, you know what? Let's make it helium. We'll make it helium. How many electrons does helium have? 2. All right, we didn't talk much about what's called Hund's rule, but when you put electrons into the subshells, one will spin in one direction first, and the second electron spins in the opposite direction. So if we're talking about helium, there's the helium nucleus. Here's the 2 electrons of helium. One of those electrons would be traveling in a clockwise direction, right? It's going to be going in this direction around. And a lot of times you'll see animations that will show incorrectly that the electrons are chasing each other in the same shell, which is not the case. What happens with electrons in the shell of helium is one electron is traveling in one direction and the other electron will travel in the opposite direction. So really what's happening is the electrons are traveling like this. So at some point in time, just for a split second, and you know that electrons travel at the speed of light, so we're talking about a tiny, tiny nano fraction of a second. So at some point in time, both those electrons are going to be on one side of the molecule. What that means is then this side of the molecule, or this side of the atom of helium is slightly negative just for an instant in time. All right? Then they move past each other, and now it's all real neutral because they're not, next to each other. And then they'll pass each other in this direction, and for another moment in time, it is slightly polar. Not very, but just a tiny, tiny bit. And that's what they call an instantaneous dipole. It's something that's normally not polar, but because of the movement of electrons traveling in different directions, right, that at some point they can be next to each other. So if you have a whole bunch of helium in a tank and it's in liquid form, that you might have slight intermolecular forces when those electrons come next to each other. Okay, that's one way that you can have what's called an instantaneous dipole. Another way you can have an instantaneous dipole is if you have another, here's a good depiction of a long chain hydrocarbon like the organic chemist might depict it. It's hydrogen are the white ones, carbon are the black ones, and you can see why they call it a hydrocarbon chain, and that organic chemistry is concerned with everything hydrogen and carbon because that's what's hooked up here, right? Hydrogens and carbons. This happens to be a pentane, 1, 2, 3, 4, 5. If you have only one, it's called a methane. 2 is ethane, propane, butane, and pentane is 5. So those are different gases depending on how many carbons are in the chain. Would you say this is polar or non-polar, this molecule? Very non-polar. There's no non-bond electron sticking out. There's no electronegative element sticking out anywhere. It's very non-polar and very symmetrical. Well, if this molecule is floating around in liquid form, right, and it comes up and bumps into another molecule, we'll just pretend this is another molecule, then it bumps up into it, for a split second in time, the electron cloud that's created by all of these shared electrons is slightly dissociated. And you might think about it sort of like if you had a balloon, and it was a really long balloon, and you smooshed the balloon on one side, what would happen to the other side of the balloon that was not smooshed? It would kind of get bigger, right? So you got a long, skinny balloon, and you smoosh it on one side, and the air is going to go whoop just for a split second in time, and it's going to be polar for just an instantaneous moment in time. So you can bump molecules in liquid form, and that dissociates their electron cloud. Well, it depends on how big of an electron cloud you have, how intense these instantaneous dipoles can be. So if you have a very small gas, something like here's a, let's see, ethane. Here's an ethane gas, or ethyl gas, excuse me. Ethyl, propyl. Okay, here's ethyl gas and propyl gas. Which one would have a larger electron cloud? A shorter hydrocarbon chain or a longer hydrocarbon chain? Longer, it's going to have more electrons. So this can create more of an instantaneous dipole. So a trend in this sort of a comparison is if you have a short chain hydrocarbon or a nonpolar molecule that's very small, it's very difficult to create an instantaneous dipole because the cloud of electrons is small. But the larger the molecule is, the more you have in your hydrocarbon chain, then the easier it is when it gets hit to create this idea of a temporary dipole. So short chain versus long chain. Another comparison. These are both, let's see, methane, ethane, propane, butane, pentanes. These are both pentanes. This one is what we call normal pentane. They both have the same chemical formula, C5H12, so there's still 5 carbons there. This is what we call isopentane. It still has 1, 2, 3, 4, 5 carbons. It still has the 12 hydrogens. So the molecular mass of these and the chemical formula would be exactly the same. They're both C5H12. They both have the exact same molar mass. But which one would it be easier, let's see if we can zoom out of there a little bit, which one would it be easier to polarize by bumping it? The long one is going to be much easier to polarize. This one is much more compact, right? So the electron cloud is all smooshed and it's very tight. If you bump this, it's like a round balloon that you smoosh on one side. It's not going to distort very much. This one's like a long skinny balloon that you smoosh on one side. It's going to distort more. So if you have a compact hydrocarbon chain versus a long hydrocarbon chain, this one would have more intermolecular forces or more London dispersion forces because of the way the molecule is oriented, long and skinny versus short and fat. All right, so if we go back, now that we've explained London dispersion forces, we look at propane, and we look at the first molecule. It's just a 3 carbon chain. All right, so very nonpolar. If we look at the second molecule in that list, dimethyl ether.
You're talking about
When you say gases in liquid
I mean-
form, everything can be solid, liquid, or gas. It just depends on what its boiling point is at normal atmospheric pressure. A lot of the things we're talking about now, if they were in the open air, would be released as gases because their boiling point is so low, the temperature of the boiling point is so low that they would be gases at room temperature. But if we can cool them off enough and put them under a pressurized container, we can keep them as gas. For example, if you've ever lifted up a propane gas container for your barbecue, and then when you're changing the tanks around, the empty one is super light, right? You put it into the thing, then you pull the full one out, and it's really heavy. And my sons used to always be curious about that. They'd be like, if this is a gas, why is it so heavy? Well, because it's in that container, which is pressurized, it's actually in liquid form. So when we're talking about these intermolecular forces, it is in a liquid form. So we have to remember that it's in liquid form. Question, yes?
So with our top one, are we labeling that as what's it called, the instantaneous dipole, or are we labeling it?
Well, the type of intermolecular force this would have in it would be London dispersion forces, and that would be created by an instantaneous dipole. If you had a bunch of propane molecules in a propane tank and they bumped each other, a few might have an instantaneous dipole. And the propane would have less of an instantaneous dipole than something like pentane. If we had a tank of pentane, it would have a higher boiling point because it has more carbons, which give it a ability to have a more polarized electron cloud. Yes?
So is this limited to hydrocarbons? Or?
No, no. We are going to talk a lot about hydrocarbons because that's what these things are. But no, anything. Hydrocarbons, it's hard. Let's go on because that's a great question, but I think this will help as we go on. All right, so dimethyl ether is the next one I want to talk about. As a physical chemist, I would just tell the formula is C2H6O, which isn't a whole lot different than propane. But as an organic chemist, how they would write it, the formula for dimethyl ether is they'd say it's CH3O, CH3. And if you looked at the molecular structure of dimethyl ether, it's got an O, and I'm going to make it look like a bent molecule here, because it is. If you went through and did the Lewis structure and counted all the electrons in this to see how everything would fit, that's what dimethyl ether looks like. Now, it is relatively symmetrical, right? So if we're looking at polarity of molecules, it is relatively symmetrical. However, what sticks out? What do you notice about this molecule that might cause it to be slightly polar? Those big lobes of non-bonded electrons in the molecule that has a bent molecular geometry around that oxygen atom. If you looked at the electron geometry around that central atom, it would be tetrahedral, right? There's 4 areas of electron domain, but the molecular geometry is bent because you've got these 2 areas of non-bonded electrons which push those 2, these are called methyl groups, push those 2 methyl groups down, creating a slightly polar molecule. So it would be slightly polar molecule, this particular one. And this particular situation here, this is called an ether group. And that's what makes this an ether. So when you go to organic chemistry, it's an oxygen atom that is bonded to 2 of these alkyl groups or methyl groups, you could call them. All right, the third molecule on that list is methyl chloride.
Is that ethyl group or ether group?
The ether group is the oxygen that's bonded to 2 of these methyl groups and has 2 of the non-bonded pairs in it. That's in organic chemistry. There's classifications of compounds in organic chemistry. One of them is alcohol, one of them is ethers. There's a lot of different classifications in organic chemistry that you'll learn when you get there. All right, methyl chloride, as a physical chemist, I would write it CH3Cl, and that's actually how an organic chemist would write it too. So finally we agree on something, the physical chemist and the organic chemist. A methyl chloride is a carbon smack dab in the middle, and it's got some groups outside on this of it. I know, what would you say about the polarity of this particular molecule? I'd say it's polar. And why is it polar? You got a big old chlorine. Remember, if you look at the trend in electronegativity, This is the trend in electronegativity. Chlorine is right up there, right underneath fluorine. There's fluorine, and chlorine is right underneath it. So chlorine is pretty darn electronegative. Plus, you've got 3 gigantic lobes of non-bonded electrons sticking out at the top here that makes this side of the molecule negative, and the hydrogens on this side are going to be slightly positive. So this one is even more polar. We go with the next group, the next molecule, acetaldehyde. Organic chemistry, everything is spelled really weird, but you get used to it. As a physical chemist, I would write this stuff C2H4O. Organic chemists would write it CH3CHO. So they give you a little bit more of an idea of what it looks like. And if we looked at the molecule here, it's got a carbon with a methyl group on one side, the CH3. And we got hooked to a C, and then we got a double bond O and a hydrogen here. And then we've got some non-bonded electrons there. This group here, this is called the carbonyl group in organic chemistry, the CHO group. Now, what would you say about the polarity of this molecule? I'd say it's pretty polar, right? Now, this one's got the chlorine sticking out just on one end. This one's got oxygen, which is super duper electronegative. Remember, oxygen is way up there, right next to, right next to fluorine in terms of its electronegativity. Plus, then you got 2 ginormous areas of electron non-bondedness over here. So not only is it on the end, but you also have non-bonded electrons. So that one's pretty darn polar too. And the last molecule is acetonitrile. What's that?
What's its molecular forces that they will have?
Well, this one, that's a great question. This one would have London dispersion forces.
Yeah.
What about the second one, dimethyl ether? I say dipole-dipole. It have slight dipole-dipole interactions there. What about this one? Dipole-dipole interactions for sure. Is it hydrogen bonding there? No, because it's not. There's no hydrogen bonded directly to nitrogen, oxygen, or fluorine. What about this one? What kind of interactions would be there? No, there's no ions in there, and unless we throw some ionic salt in there and had some ions floating around. So just be still dipole-dipole. Would these dipole-dipole be stronger than these dipole-dipole?
No.
Yes, this is more of a polar molecule. It's also heavier. It's bigger. And so the heavier and bigger makes a difference too. Thinking about it, if you have a big heavy molecule that you want to lift out of the liquid form and throw it up into gaseous state, it's going to be harder to do that than if you have a light molecule in liquid form and you want to get it out of the liquid and throw it up into gaseous state.
Considering the electronegativity of the chlorine?
Even that, because this one is heavier, but it's got a larger dipole moment associated with it, yes.
Heavier, more polar, so although most of these are gas at room temperature, the acetaldehyde will have a higher boiling point than.
Yes, because it is more polar, which means it's going to take more energy to vaporize it and change it from a liquid to a gas. You have to think about these intermolecular forces like magnets. If molecules were magnetized in a container, it's going to be harder to get them to leave the container than if the molecules are not magnetized, right? They're just plain molecules. And the heavier they are, the harder it is to get them to leave. All right, acetonitrile, as a physical chemist, I would just call this C2H3N. The organic chemists give you more of an idea of how it's put together, and that's how they write the formula. How this thing looks like, once again, it's got the methyl group on one side, but now you bond to a carbon, and then you triple bond to a nitrogen, and then the nitrogen's got a set of non-bonded electrons on the very end. What would you say about the polarity of this particular molecule? Really, really super de-duper, like Barney would say. This one is super de-duper polar. Polar of all, the most polar of all the molecules that we've talked about. So let's go back now and look at that list. And I think this helps give us some context into why this is true. Once again, if we looked at the molecular weight, they're not that much different. The dipole moment, that tells you how polar each molecule is. That first one that's just that long hydrocarbon chain has almost no dipole moment at all the way to the one that we decided was super duper polar, which is acetonitrile. Now the boiling point, remember, That's Kelvin temperature. How do you get to Celsius, which is something you're more used to? You got to subtract 273. So 231 minus 273 is a negative number. So what temperature does propane boil at? Below 0 degrees Celsius, right? It boils at a temperature lower than the freezing point of ice. So that gives a little context. These are things that we're talking about in pressurized containers. Dimethyl ethers, and so you can see what's the trend in the boiling point there. They're increasing from this one is the lowest boiling point to this is the highest boiling point, and that's because of the intermolecular forces. You got to think about them like little magnets. Even though they're almost all the same molecular weight, the ones that are more polar are going to cost more to vaporize. All right, here's good examples of hydrogen bonding. And once again, this is where they start using these little dots. We've got dots that are supposed to represent electrons, which is one type of symbolism. Now they use the same darn dots to show intermolecular forces, which also makes me crazy. I had a discussion with my colleagues. There's an exam. How many people took Chem 130 in this class? From this college somewhere. Okay. Did you guys take the final exam in Chem 130? All right. One of the problem questions we were discussing as a department in the Chem 130 final exam is a question that relates to intermolecular forces, and they use this dotty thing to represent the intermolecular forces. And the question is something like, what are the red dots supposed to represent? Okay. How confusing is that? Well, no wonder it's a problem question that a lot of students didn't get the answer right to, because it's just a poorly worded question. Not everybody understands that these dots can mean different things, the different symbolism. So that's what they're trying to show you is the intermolecular forces between the positive portion of the molecule and the negative portion of the molecule. So hydrogen bonding occurs in ice, which is actually pretty interesting. When ice is at, say, 80 degrees, you could jump in the water and the molecules would be moving relatively quickly. As the water temperature decreases, what happens to the speed of the molecules? If we went from 80 down to 70, they're going to slow down. What would you predict happens to the density of water? Remember, that's how many grams in a certain amount of space. If the molecules are slowing down, how would that change the density of water as the temperature decreases? Density would increase because the volume would decrease, right? Since they're moving slower and they're moving closer together, then the volume decreases. Let me show you that a little bit more graphically. If we had our water molecules, we're going to pretend these are two water molecules, right? They're moving around in liquid form quickly, and then as they slow down, they get closer and closer, and then once they get to the point of between 3 and 5 degrees Celsius is when they get close enough and slow enough to each other that hydrogen bonding takes over, and instead of the water getting more and more dense and the volume decreasing all the way down to 3 degrees, once this hydrogen bonding takes over, the water molecule, it's spread apart. And so the density and the volume actually increases. I'm sure you've seen this. When you freeze ice, if you fill up a tray with water and then you put it in the freezer, are the ice cubes the same size as the original water you put in the ice container? No. What happens to those? They expand. They get bigger. And that's what causes weathering in rocks. Water goes down in between the cracks of rocks, and the water freezes and expands, and it cracks the rocks open, and then erosion carries the bits of rocks away. So this idea of water freezing is super important. Another reason it's super important is we would not be on the planet today if hydrogen bonding and these intermolecular forces did not take place. And here's why. We've got a lake in the summertime. Sun is shining, flowers are growing, right? Everything's nice. We've got a happy little fish swimming in the lake. All right, it gets colder. All of a sudden the sun goes away, winter comes, fall's here, and not in Arizona, but in other places when it gets really cold, the lakes freeze over, right? The lakes freeze over. What happens is the water molecules get closer and closer and closer together, but then all of a sudden when it gets down to between 3 and 5 degrees, the density increases, and what happens to the ice? When you put ice in your drink, does it sink? No. Every other substance besides water, if you put the solid form into the liquid form, the solid form will sink. Ice is unique in that the volume expands because of this hydrogen bonding idea, and the density is actually less, and that's a good thing, because when lakes freeze over, if this wasn't true of water, the lakes would start to freeze over in the bottom, right? Because the densest water would sink down to the bottom. As the lake freezes over in the bottom, all of a sudden our fish would go from having a dot eye to having an X eye, right? He would be dead. He would be frozen fish sticks in the lake, and we wouldn't have been able to crawl out of the primordial soup and become humans. All right? So it's a good thing this happens, because in the wintertime, here's the lake, the water freezes just at the top because ice is less dense. It floats up to the top, and it creates a little blanket. So I'm going to make a smiley face on the fish. He's a little chilly. But he can stay down there, and the ice actually acts as a very good insulator. It insulates the water from the coldest atmospheric conditions up here, and you can take it. My grandma has a farm in Minnesota, and a popular sport, if you could call it that, I would call it more of torture, is ice fishing. And you get this little house, it's called an ice house, and you pull it out on the ice, and it looks about the size of an outhouse, and you drill a hole in the ice, and you lift the hole out, and then you drop a line in the water, and the fish are starving because there's nothing out there, it's all frozen over, and as soon as anything comes down through the ice, bam, you got some fish, and you just got to get them up through that hole quick enough, and they flap around, and they, sometimes when it's so cold, you can just open the door of the ice house, throw the fish out onto the ice, and then when you're done fishing an hour later, they're all frozen, and you just bring them home to your freezer. So there you go. When you live in Minnesota, that's the kind of recreation you have. But this would not be possible if ice did not get less dense between 3 and 5 degrees, and that's all because of hydrogen bonding. It opens up the molecular structure, allows air in, and keeps the molecules a little bit further from each other, so that the ice, when it freezes, goes to the top of the lake. All right, so now you can answer that question. Is why doesn't the ice freeze up from the bottom? Yes?
But you were saying that the ice kind of floats up to the top, but wouldn't it also, because you were saying the other day that for surface tension, those molecules are closer together at the top because...
That's a good question. I don't know how those two things would interact, because you're right. Surface tension creates the ones at the top to be closer, but phase change is a different interaction that probably would destroy the surface tension, because surface tension is a relatively weak intermolecular force, but when something goes from solid or from liquid to solid, that crystalline structure is going to be a much stronger structural formula than the intermolecular forces. But I never thought about that. That's actually a good point. All right, London dispersion forces. We talked about the two ways. Here's the helium atom with the electrons that could go in different directions and end up on the same side of the molecule. And then we talked about the two molecules, the long skinny molecules having longer, more polarizable chains versus short stumpy ones. This would be the normal pentane. This is the neopentane. There's propyl alcohol versus isopropyl alcohol. You guys have all seen isopropyl alcohol in your home, right? That's the same thing as propyl alcohol. It's just that the hydrocarbon chain is hooked up a little bit differently. All right, now we're talking about London forces. Now we're talking about molecules and substances that are very non-polar. Okay, noble gases are all monatomic molecules, single molecules. The molecular weight increases top to bottom. Boiling point increases. Okay, if we're just looking at the noble gases, the monatomics, why do you suppose the boiling point is increasing as the molecular weight increases? What causes it? Size has part of it. What else? It's heavier, right? It'd be harder to get a big beefy atom out of the liquid and throw it up into the air and boil it. What else? The bigger ones have what? More electrons, which then can create a more polarized electron cloud, creating a more intense, instantaneous dipole, right? Instantaneous dipole. These are all non-polar molecules. F2 is just two fluorines hooked together, two chlorines, two bromines, two iodines. I believe those are all single bonds in between them. The molecular weight increases, same thing. Boiling point increases, because they're larger molecules, they're heavier, but also each has a larger electron cloud around them because they have additional shells and energy levels. Larger electron cloud creates the possibility of a more polar instantaneous dipole. There's another way to summarize intermolecular forces. And now let's talk about some of the different physical properties. Boiling point is something that's relatively easy to understand because we've all seen things go from liquid to gas. But now we want to talk about some other physical properties that you might not be as familiar with in the context of what the word means. A good one is viscosity. All right, if any of you have used oil or if you've changed the oil in your car, there is a viscosity rating on oil, 10W30, 20W40. There's numbers, and they have to do with the viscosity of the liquid. For example, viscosity has to do with its ability to resist flowing. So viscosity, you should write this definition down because that's something you have to think about when you're just thinking about viscosity. Viscosity is the resistance to flow. The resistance to flow. For example, molasses in North Dakota in January, and you're trying to pour it out of a jar, is it going to have high viscosity or low viscosity? Very high. It's going to resist flowing a lot because molasses already is pretty thick, right? And if it's in North Dakota in January, it's going to be especially thick, so it's going to have very high viscosity. We take that same molasses here in Arizona in July, is it going to have high viscosity or low viscosity? Very low viscosity. It's not going to resist flowing at all because it's going to be very fluid. Viscosity is helpful in automobile engine oil. When I lived in Flagstaff as an undergraduate, I would have to change my oil in the spring and the fall, and that's because I would live in Arizona in the Phoenix Metro Valley area in the summer months, and I would move back to Flagstaff in the fall. Do you think you would want a high viscosity oil in Phoenix, or would you want a high viscosity oil in Flagstaff? Would you want it to resist flow in Phoenix, or would you want it to resist flow in Flagstaff? In Phoenix, right? You want it to be more flowy in Phoenix because it's much, wait a minute, no. We want high viscosity in Phoenix because it's so doggone hot that the heat increases the viscosity, right? So, or the heat decreases the viscosity. See, I need to think of the definition. Viscosity is the resistance to flow. When it's hotter, it decreases the viscosity. It flows more, right? So you would want a high viscosity, something that resists flowing a lot in Phoenix, where you would want low viscosity in Flagstaff. You want an oil that's going to be easier to flow because it's colder, right? It's colder in Flagstaff. We used to do an experiment with viscosity when I taught high school chemistry. We would take different hydrocarbon oils. I think we had things like kerosene and different gasolines, as well as like diesel fuel. And we put them in these big test tubes, and we put a marble in each of the test tubes, and we would seal the test tubes. And then we would take the test tube that had the fluid in it with the marble at the bottom, and we'd have students turn the test tube over and count the seconds till the marble went from one side of the test tube to the other. And that was a good measure of the viscosity. So if it had high viscosity, would the marble take a long time to descend, or would it take a long time? Short time or long time? If it had high viscosity. Right, it would have a high resistance to flow, so it would take a long time for the marble to move down from the substance itself. So viscosity increases with stronger intermolecular forces. So if you have something like hydrogen bonding, the viscosity is going to be very high. It's going to resist it. We actually used to do an experiment when I taught high school chemistry that would show viscosity. We'd have students take a plate of glass, and they would put 3 drops on the plate of glass. And 1 drop was alcohol, 1 drop was oil, and 1 drop was water. All right. Oil is very nonpolar substance. It's a hydrocarbon chain, generally, and so it's not going to be very polar. Alcohol is slightly polar, right? What would you say about water? Is it polar or nonpolar? Polar. Really polar, like super polar. All right, so we put a drop on a glass plate. Then I would have the students, they'd have the glass plate flat, and then they would turn it up on its edge. So here would be the glass plate with the 3 drops, and you would turn it up on its edge slowly. So you would slowly bring the glass plate up on its edge, and this would also be a good measure of viscosity. Which one of those things do you suppose would slide down the glass plate first?
Alcohol.
The oil. The oil would slide down that plate first. Now you can't just go immediately, right? You have to do it slowly like this, and you would see at some point that the angle would be significant enough that one would start to flow. It's the oil that flowed first. What would be the next thing that would flow? The alcohol would be number 2, and then water would be number 3. Now, if you took that same plate of glass before you tipped it, and here's the side view, right? So if you got your eyeballs on the edge of the table, right, and you're looking at the side view, and we looked at the alcohol, the oil, and the water, the drops of them, the water droplet looks like that. The alcohol, same size drop, would look like that, and the oil would spread out over the surface. Why does water have such a nice rounded, and actually if you look at it, it like tucks itself up under the edges. And alcohol still stays in a nice drop shape, but it doesn't have this nice little tucked up edge. What do you suppose is happening there? Surface tension. Surface tension is causing the water to, on the very edges, right, because they're all being pulled from the inside, right, it causes it to tuck it up a little bit. These both have hydrogen bonding in them, but this one is a much stronger hydrogen bonding than this is, and that's why it remains. Now, if you did an evaporation test, now of course, the oil is not really going to evaporate hardly at all. It's just going to make a kind of a slimy mess. Which one of these would evaporate first? The alcohol would evaporate first. Why is that? It's less polar of a molecule. Water is much more polar, which means they're going to be more magnetic. They're going to be holding all the molecules down as a liquid more. If they're not holding it quite so hard, then it's easier for alcohol to vaporize. That was kind of a fun test. So viscosity is a resistance to flow, and evaporation also is a good measure of things like surface tension. Right? We talked about surface tension. Now, phase changes. Most phase changes, and I like this diagram. This is an energy diagram. And if you look at the energy of the system, meaning the highest energy things are going to be up here, the lowest energy things are going to be here. The distance between solid and liquid is very small, and that's because the phase change between solid and liquid is generally less of an energy requirement than the phase change between liquid and gas. Now, if you have high intermolecular forces, this difference is going to be much bigger. If you have low intermolecular forces, this difference is going to be much smaller. Those things are going to be much closer together. And this next slide kind of shows that, right? So here's something, these have low intermolecular forces, much higher intermolecular forces. Water, look at the intermolecular forces water has. 6 is a measure of the heat of fusion, the amount of energy it takes to turn something from a solid to a liquid. 41 is a measure of liquid to gas, so it's like 7 times as much. 7 to 29, 5 to 24. So those are the amounts of energy required to do either phase change, and that is associated with intermolecular forces. And we did some calculations after Chapter 5 or in Chapter 5 that had to do with this, so you don't have to do them in this particular chapter. Finally, we get to this idea of vapor pressure. Now, this is something that I'm going to give you a really specific, any questions that you get on the quiz that you're going to take in this class on Thursday, or on the exam that you take over Unit 4, or the final exam, they're going to ask you questions about vapor pressure. And so I want you to think about vapor pressure in a really specific way that I think will be helpful when you're trying to describe what things have more or less vapor pressure. Okay, so vapor pressure. This is how I want you to think of it. You have to think of a closed container. All right, so here's our closed container. It's closed to the atmosphere, and in this closed container we have stuff that's a liquid and we have stuff that's a gas. So it is existing as both liquid to gas, and we have what's something that we haven't talked about in this class, but when you get to Chem 152, you talk about a ton, this idea of an equilibrium. What that means is you have liquid changing to gas, but then some gas is also changing back to liquid, and the rate of liquid to gas or gas back to liquid is the same. So it is at equilibrium. So I'm going to draw some gas particles up here, because that's how I want you to think of it. The liquid particles are going to be very, very close together in the context of this closed container. I want you to think of the gas particles as being far apart. Now we would have a pressure gauge that would be in our container. So this is the pressure gauge. And the pressure gauge just gives you a measure of how many of these little pieces are in the gaseous state. What actually causes atmospheric pressure? When I say I'm measuring the pressure of something, what's causing that pressure to occur that I'm trying to measure?
How many molecules are there?
It has to do with how many's in there, but what are those molecules doing that's causing the pressure? They're hitting each other. They're hitting each other, or they're hitting the sides of the container. So a pressure gauge measures how often the molecules are hitting each other or hitting the sides of the container. So if you have more molecules, or they're moving faster, what's going to happen to the pressure? It's going to increase. If you have fewer molecules, or they end up moving slower, then the pressure is going to do what? It's going to go down. All right, so now we have to think about this idea of pressure. If I have something that has very high intermolecular forces, for example, something like water, what would the vapor pressure measure here in, say, like water versus alcohol versus, we'll say, oil? We'll use our last example. All right. So I have one container of just water. I have another container, a separate closed container of alcohol, and a third separate closed container of oil. And I'm able to, and they're all the same temperature, right? You have to have that as a control in the experiment. So you have a container like this of water, another container like this of alcohol, a third container like this of oil. Each one would have a separate pressure gauge on. They'd all be at the same temperature. Which one would have the highest measurable pressure? I would say alcohol. Let's take oil out of the mix. Let's just compare these two right now. Water versus alcohol. Which one would have a higher vapor pressure? The alcohol would have a higher vapor pressure. Why is that true? Why would it have more atoms existing as a vapor than has a lower boiling point? Lower what? Lower polarity. We're getting there. Lower intermolecular forces, meaning they're not as magnetic. So if you have a container of alcohol with fewer intermolecular forces, it's easier for those molecules to escape the surface of the liquid and become gaseous than it would be for something like water, which would have a much lower vapor pressure, which makes sense. When you're in the hospital, what do they put on your skin to cool you? Do they put water? No, they put alcohol. And how does alcohol feel when you put it on your skin? If it gets in a cut, yeah, it burns. But I mean, if you don't have a cut or chapped skin, what does it feel like? It feels very cool, right? Because what's happening when you put that alcohol on your skin? It's evaporating. Where's it getting the energy to evaporate? From you. And it's easier for it to evaporate because it's not as polar, so it evaporates quicker, pulls that energy from you quicker, and cools your body temperature off faster. Which makes sense. Like in the summertime, especially in Arizona. I used to live in a house with a pool, a giant money pit. That's what a swimming pool is in Arizona in the summertime, because chlorine gets used up so quickly because the water's so hot. Holy crud. That was a giant money pit. Anyway, swimming pools are super cool, and they're fun to have. But when you are in Arizona in the summertime and it's 120 degrees outside, and you look at the temperature gauge of the swimming pool, it literally could be like 95. I've seen a swimming pool, and it's not 95 Celsius, we're talking Fahrenheit here. So it's 120 outside Fahrenheit, and 95 in your swimming pool. You jump in, you're like, oh, okay, well that was marginally refreshing. right? Because it's not much of a temperature difference. But then you get out of the swimming pool and you feel cold. But it's 120 outside. Why all of a sudden do you feel so cold? What's evaporating? The water on your skin. As it's evaporating, where is it getting that energy to do so? From you. It's pulling that energy from you to evaporate and change phases. When do you start feeling hot again? After you get out of the swimming pool. Once you dry off. So then you jump back in again. And that's something that, you know, as an Arizonan, I've always realized that evaporation is such a good cooling process. They used to have canteens when I was a Girl Scout back in the Stone Ages, and these canteens would have fabric on the outside of them, and the fabric, it felt sort of flannelly, and it was kind of thick fabric. And you could take the canteen, we used to do crazy stuff like hike in the desert. I still don't understand how people want to do that, hike in the desert in the summertime. Anyways, we'd do crazy stuff like hike in the desert. And we would have our canteens, and if your water was warm in the canteen, all you had to do is dip it into something. It didn't have to be cold water. Dip it into water. It would wet the outside of the canteen, which was aluminum, which has a very high heat capacity, right? Which means it transfers energy very efficiently. So the canteen was made of aluminum. It's light. It has a high heat capacity, transfers energy really well. As that fabric on the outside of the canteen cooled, where was it pulling the energy from?
The water.
The water in the canteen. The aluminum made a very good conduit because at high heat energy, or high specific heat capacity, move that energy out of the canteen very rapidly. By the time you got halfway in the desert, you open your canteen, it was almost really, really cool, like almost ice water, because and as long as you kept getting it wet, it would continue to pull the energy out. Great way to defrost meat. If you've ever seen on TV, there used to be this thing, it was a instant meat defroster, and it has a hunk of metal, and you plunk your frozen steak on this hunk of metal, and it defrosted almost instantly. You know what that hunk of metal was made out of? Aluminum, because it has a high heat capacity. It moves energy very rapidly. You know what's even better than aluminum? Aluminum's heat capacity is something like 0.87 something. What's water's heat capacity? 4.1A, like 5 times as much. Fill up your sink with water, throw them, if it's in a plastic container, right? Put the meat in there, and in 10 minutes it'll be defrosted. You don't need to buy the 1995 hunk of aluminum on, as seen on TV. You just use a sink full of water.
Alcohol has a higher vapor pressure because of lower
Intermolecular forces, right. So that's a good way to think of it. The higher the intermolecular force, the lower the vapor pressure is going to be. Right? So, interesting facts. All right. Here's interesting charts. I like this chart. Diethyl ether, ethyl alcohol, water, and ethylene glycol. Ethylene glycol is a oil. Water, ethyl alcohol, and diethyl ether. These are what we would call vapor pressure curves that are dependent on temperature. And this is how much vapor's in the air. Remember my tool that I said we could measure vapor pressure with, this closed container? All right, so if we had these substances in closed containers and we measured the vapor pressure at different temperatures, right? So here the temperature's low, here the temperature's high, here the vapor pressure is low, the vapor pressure is high. What happens to vapor pressure of most substances as temperature increases? Vapor pressure is going to do what? It's going to increase. Okay, well, why is vapor pressure increasing as temperature increases? Why is there more of those pieces up there as a gas if you increase the temperature of the entire container? You're getting more of the liquid going to gas faster than you are the gas coming back to the liquid. So what you're actually doing is you're upsetting this equilibrium. You're making this equilibrium go bigger, right? And this one doesn't change much. And so it looks like you have more up here. Well, you do have more up there because you have more particles in the vapor state. So this is just a measure. So why do you suppose, let's just look at these three, diethyl ether, ethyl alcohol, and water. Which one is affected most by an increase in temperature? Which one increases its vapor pressure most rapidly? The diethyl ether. The curve, if you could, you did a regression on this curve and you analyzed it, the value here would be much higher than the value over here. Why is the curve on water so low? more intermolecular forces. They're like little magnets holding them together. All right, now I'm going to try. Go ahead.
Where's that ethylene glycol plant? That's antifreeze, I think.
Yes. Yeah, oh, that's right. Ethylene glycol is antifreeze. That's a great question. Let's look at what's the molecular structure of ethylene glycol. It must be either really polar or really heavy. Google knows everything. All right. What is the molecular structure of ethylene glycol? Well, there it is. You got two OH groups on it. You would think that would make it pretty polar. Oh, I know what's going on there. What kind of forces are in that? Hydrogen bonding. How do you know it's hydrogen bonding? Right, you got and then you got hydrogen bonding on each end. So that's probably making ethylene glycol even more polar. Plus, it's also a lot heavier than water. Water's just H2O, and ethylene glycol has got 2 carbons, 2 oxygens, and then quite a few hydrogens. So that makes a difference too. So the mass of it. No, good question. All right, I'm going to try and do a demo now, but in order to do the demo, what I have to do is I have to unplug one source of media. So what I'm going to do is I'm going to unplug the ladybug. Actually, before I unplug the ladybug, I'm going to show this so that everybody can see in our recorded audience what it is that I'm going to be using here. Let me go over to the ladybug and show you. I'm going to do a quick demo here. I've got a vernier temperature probe. In addition to the vernier temperature probe, I have some substances in test tubes: isopropyl alcohol, acetone, and then I'm going to put just plain old water in this last test tube. All right. So in order to do that, I've got to combine my isopropyl alcohol because it must have vaporized in the. Oh, was not allowed to do any demos except with water under 80 degrees or household chemicals. So since isopropyl alcohol and acetone is basically fingernail polish remover, I was able to get clearance, so silly, to do demos in class. Whoop, whoop. I used to do demos all the time, but then my chair said, you don't have running water and there's no fire extinguisher, so can't do it. All right, so now I'm going to have 3 test tubes full of liquid. And what I'm going to do with each of the test tubes independent of another is first I'm going to rinse off my probe so that it's completely clean. Then I'm going to take the probe and I'm going to put it in each one of the substances down in the test tube. So I'll open up the test tube. I'll put the probe down into the test tube. I'll pull the probe out, and then I'm just going to allow the probe to be open to the air. All right, so that's what I'm going to do with each of the demos. So now I'm going to unplug the ladybug and plug in. Yep, I know that. Plug in the vernier stuff, which you guys have used before. Well, I had a heck of a time downloading the software for vernier onto my computer. I had to get help from the IT guys. I tried it twice and we finally got it done. Let's hope it works. All right, looks like it's working. And let's see if I can change the temperature. I'm putting the thermometer probe into my arm crease now. Yep, and the temperature went up. Okay, so there's our time temperature. And now the first one I'm going to do is I'm going to take, well, we'll try the acetone first. We'll try the acetone first. Okay, so we're going to take the thermometer and I'm going to put it in the acetone first and allow it to come to thermal equilibrium. So right now we're just measuring the temperature of the acetone. So let's see. Collect. There we go. Yeah, the heat from my hand. I'll just keep my hand away from that. So the temperature, I haven't pulled it out of the substance yet. I'm just letting the temperature probe take the temperature of the acetone and allow it to come to thermal equilibrium. So it looks like it's about 24.5. All right, now I'm going to take the thermometer out of the acetone. I'm going to hold it up in the air. And you can see what's happening to the temperature. Temperature's going down, right? Temperature's going down. And why did it stop going down? There's no more of the acetone on there. What would you, if we let it go, what would you expect to happen to the temperature probe over time? It's going to warm up to like room temperature, right? All right, so we're going to stop, and then we're going to save this data. So
You can save it on the third button there.
the experiments button,
No, down. Below experiment.
below experiment.
See the big fat button in the second toolbar.
The floppy disk.
That one?
Yeah.
Yeah, that.
Okay. Oh no, I want to save it on the same graph. There's a button that you can use to save it on the same graph.
Then he's gonna open a new page.
No, I think it's store latest row. There it is. Okay, so the second one, I'm going to rinse off
It's still there.
my probe. You know, I want to keep it there because I want to compare all three of the, I want to make a new curve. And what it'll do is it'll make the new curve with a different color. All right, that was acetone, right? So now we're going to use the isopropyl alcohol. So now I'm going to put it into the isopropyl alcohol. I'm allowed to collect. I'm allowed to come to thermal equilibrium. I'm not going to still just taking the temperature of the isopropyl alcohol in my hand. Come to some kind of thermal equilibrium here. Still in the solution. I haven't taken it out yet. I might have to. I want it to stabilize. I don't want it to keep going up. So I'm not going to take it out until it stabilizes and stops going up. Still going up a tiny smidge. And this lends credence to the idea that all three of these liquids were in the stock room and they're all probably at the same temperature. It's just a question of taking the temperature before we start. I would bet that blue line's going to get to what point? Probably about the same point as the red line started, right about in here somewhere. So we're almost to that point. Just got to get to the temperature. All right, I'm going to take it out now. We can look at the curve there. It's almost stabilized. Okay, here we go. Taking it out. Cap going. First one was the acetone. This one is the isopropyl alcohol. Now, which one, if you had to describe each of those curves, the curves that are going down, which one would you say would have a steeper slope? I would say the first one has a steeper slope. The second one, it's not as steep, but it was longer, right? Lasted longer. And I think at this point we're at the point where we're done. Okay. So now, what would you predict about water? Store the latest run. There it is.
It's gonna have less steeper, but longer.
You think? Let's see what happens. Well, which one of these is more polar? Is the isopropyl alcohol or the acetone more polar? Yep, second one's more polar. It has more intermolecular forces because it took it longer to evaporate. The cooling curve was shorter. All right, here's the water. Start collecting with the water. The water's the third line. And it's probably got to, it's got to come to thermal equilibrium. Oh, I should have that over there. Normalize here. Oh, okay, that's about right. So now we'll take it out. What would you say about water slope now? Is it the steepest or the most gradual? The most gradual. Why is it the most gradual? The highest intermolecular forces of all. And what kind of intermolecular forces does water have? Hydrogen bonding. Right? Okay, that's it for today.